Hello, I hope I'm
Yes, ma'am.
audible. Really
Is
sorry,
it
sir,
is
for the
it is
delay.
it is it is it working now?
Yes, it's working now. I think, yeah,
Okay.
it's working. Thank you so much for waiting. Yeah, I just,
I'm okay. Okay, right, ma'am.
you want to say something?
No, 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 please continue, ma'am.
Okay, sir. Thank you so much. Fine. So, today we'll be discussing more on stratified sampling and allocation of variables under several schemes. Now, I'll start with the basics and then we'll move on. So, last week we discussed what do we mean by stratified sampling. So, the case is um, if instead of sampling uniformly, if we have some inherent structure in our data and then want to we want our sample to somehow capture that inherent structure, then the best way to do sampling is to uh, follow a stratified sampling scheme. For example, if my uh, data of interest is, let's say, height of a person. Now, somebody in, uh, let's say, the western part of the world and somebody from the central and somebody from the east, let's say. So usually we see that there's a I mean, these heights, usual, or I could say average height, actually differs across different parts of the region. Okay, now if my question of interest is average height of the world's population, if this is the question I want to address, and if I am only sampling from India, let's say I sample n individuals, then will it be representative? Most likely not, because we as Indians have a certain kind of height, but people usually from the Western world, they are, they have usually more height than us. And also this height uh, thing is also stratified between the sexes, like females generally have lower heights than males, and also it varies all across geographical regions and different nutritional habits, food habits, all sorts of things. So the essence is that we have different strata. So if this is my world population, then some individuals are clustered around here, some individuals are clustered around here, some individuals are clustered around here. So instead of taking sampling from overall, where we have no control, like we could get random samples from, like if we do an SRS, WR or WOR, we may or may not have proper representation. Okay, so what is the way out? So way out is stratified sampling. And how do we do that? So we if this is the entire pool and this is my S1, this is my S2, and this is, let's say, my S capital H, then from each of these I draw a random sample. Okay, so I draw N1, N2, NH, and let's say in total I have N1, N2 and NH. So from each of these stratas, we call these as stratum. One is called stratum and the collection is called strata. So from each of the stratum we collect a subset of N1, N2, NH, and we follow a simple random sampling. Now we have learned up till this much in the last class. Now the question is, does it have to be equal? What happens if it is not equal? Then what else can we do? Okay, so this is what we are going to discuss in today's section. But before I move on, is there anything you want me to touch upon from the last few sections? Then I'll be happy to do that.
Please go ahead, ma'am.
Okay, sir. All right. So now that we have this, we can think of three solutions as of now to this allocation. The first one is equal. So for each stratum, so for S1 to SH, we select in a manner such that if I have to select n samples in total, then we try to select n by h. Okay, if we do this, then what are we essentially saying? We are saying that we are collecting equally from each of the stratas. Okay, the next one is proportional. Okay, now when we want to do proportional, we want to allocate in such a way such that NH is proportional to capital NH. This is what we are looking at. I'll use small h for all h equal to 1 to capital H. Okay, and if I want to do this, then I can write it like small n h is equal to, let's say, C capital NH, where C is the constant of proportionality. So then summation NH, h equal to 1 to h, equal to summation h equal to 1 to h, C capital NH. C is a constant, so it will come out. So h equal to 1 to capital H, NH equal to Cn. And here we have small n. So therefore capital C will be small n by capital N. And therefore each small nh equals to n by capital N into nh. If we follow this one, then we are actually following a proportional scheme. Okay, this looks like a reasonable choice and is operationally also convenient. Now we have another solution. So this proportional thing accounts for varying sizes. So proportional allocation accounts for sample size. Okay, now why do we care? Why do we care about the sample size? Because if sample size increases, cost of collection also increases. Okay, so let's say if you want to sample 10 individuals, the cost could be in terms of money, it could be in terms of time, it could be in terms of resources, anything. Okay, so I am bundling all these things with in a category which I call as cost of collection. Okay, now sample size is directly proportional to cost, and this part will be taken care of if we do a proportional sampling, proportional allocation. But apart from cost, another important factor that we should also keep in mind is that is variability in the data. Okay, this is also an important concept, and turns out that size of the sample size is inversely proportional to the variability. And it makes sense because if you have an estimate from 10 individuals, okay, you have some y bar, and if you have the same estimate from 1000 individuals, you would be, I would be preferring this more. Just imagine going through a Zomato review or something like that, Google reviews. If you find 10 individuals who have said that this place is good, this food is good, the amount of trust you would put on that compared to if you see 450 500 reviews, and out of which 700 and out of which suppose 400 450 people have said that yes, this place is good, you are more inclined to believe the second option, right? Because that increase in sample size would lead to less, it is expected that it will have less amount of variability. Do I make sense?
Yes, ma'am.
Okay, so the proportional allocation will only will only take care of the cost thing, but it will not, it it fails to account for the changes in the variability. So in order to do that, we need there exists a different form of allocation which is called the Neyman allocation, or also oftentimes it's known as optimum allocation. So optimum allocation is taking care of cost and variability. Okay, and how is it doing that? So in case of optimum allocation, we say that NH is directly proportional to capital NH, that is the number of sampling units present in the population, and it is also proportional to the variability. Okay, so again, if I say NH equal to C capital NHSH, or I denote it as C star, then small n equal to summation H equal to 1 to H small nh, which is equal to C star summation H equal to 1 to H capital N H and into SH. Okay, so then the constant of proportionality C star can be said as summation small n by H equal to 1 to H capital NH into SH. So therefore small nh is small n by summation H equal to 1 to capital H capital NH capital SH into SH. Sorry, NHSH. Okay, this is what we call as Neyman allocation. Okay, but this one, in order to do that, we need to know this quantity. The others are known. So if we are going with a Neyman allocation scheme, then we will have to know what is the variability in each of the stratum. Okay, so given this, we'll have to see what is our scheme of allocation and then take or draw samples from the respective populations or strata. Okay, and it turns out that if we follow this Neyman allocation scheme, then variance of y bar st is less than or equal to variance of proportional y bar st, and which is less than equal to variance of y bar st if we only do a SRS, or I should not say y bar st, y bar. So in general, stratified stratified schemes are more precise with less variability than SRS, and within stratified, Neyman more precise than proportional. Okay. So this proof has been given in the lecture. So if you want, you can go ahead and do that. I'm not repeating it because we'll anyway be solving some problems and where these variance terms will come into play, so that way we'll be able to brush up. All right, fine. So now that we know how to do this, let us solve a few problems on this thing before we move on to looking at how it is implemented in R. All right, is there any question as of now? Sir? um okay, I hope I'm audible and you'll be able to listen to this. Can you see this thing, the question on screen? Okay, so the question here is, a university has a total of 600 students consisting of 100 undergrad, 200 graduate students and 300 doctoral students, and they want to conduct a survey on academic satisfaction to draw and is expected to draw a sample of 60 students. The sampling method to be used is equal allocation, which means that sample will be equally distributed across each groups. So how many undergrad, grad and doctoral students will be included in the sample? So here small n is equal to 60 and capital H is equal to 3, that is undergrad and doctoral. Okay, so therefore each group will have equal number of samples. So this is like a no-brainer. 60 by 3, we'll have 20 from here, 20 from here and 20 from here. Okay, but if we want the same thing as proportional allocation, then the sampling scheme, or the number of samples in each group, small nh, is nothing but capital NH by n into small n. Okay, so what will it become? So this will become for undergraduate, NH is how many? 100. Capital N is how much? Capital N is 100 plus 200 plus 300, that is 600. So this is 600, that is 1/6.
Each group, how many undergraduate students included in this sample? One by 6, so 2 by 6 means 1 by 3, so 20. Doctors is 300 by 600 is 1 by 2.
Okay, so this
Yes.
into small n, we are missing that out. Small n is 60. So we'll have 10 students from undergraduate studies, 20 from graduate, and 30 from
30 from
doctoral.
doctors.
Okay, now next thing, how to do this if we have name and allocation. So name and allocation is small nh is equal to small n into nhsh by summation h equal to 1 to h nhsh, right?
Yes.
So
Yes.
then this will be for undergraduate. So let us calculate summation nhsh. So nhsh is 150 into s1 is 5, assuming variance. Okay, so variance is sh or sh square, that thing we'll have to check. So variance is actually si square. Okay, so um, for the time being, let me assume that this is actually the not the variance, but let's say, or I could even assume variance. So si square is this 5, 4 and 2. So then this would be 150 into root 5 plus 200 into root over 4 plus 150 into root over 2. Okay, let's say for ease of calculation, let me just make this a whole number. So instead of 542, let us have some squared. So let's say 25, 4 and 1. Alright, so this is just for the sake of computation I'm doing, because I want an answer which is a whole number, because a fraction sample size doesn't make much sense and we'll have to do a lot of adjustments which I don't want to go to. So this would be summation nhsh is 150 into root over 25 plus 200 into root over 4 plus 150 into root over 1. Okay, this is summation h equal to 1 to h nhsh is equal to this thing. So this is equal to 150 into 5 plus 200 into 2 plus 150. So 750 plus 400 plus 150. So this will be something around 1200. Okay, so for undergraduate, this will be 60 into NHSH is 150 into 5 by 1200. How much will it come to? Oh, okay. Here again we are running into some integers. So let's say, I mean, I don't know, 10, 10, 10, 10, 2, 15 into 5 by 2,
75,
75 by 2,
10.
something like this. Graduate would be 60 into 200 into 4 into 2 by 1200. So this is
20,
1200
10,
into 2,
20, 20,
20, and doctoral will be
60 into 150 into
1.
1 by 12. So 60, 20. 20 again, and this will be fractional. 20, 150, 7.5 into 1.
So it's something close to 7.5 or something like this. And this will be 32 point something.
Yeah.
Or no, 30, not 32, 35, 36, 37.5 or something. So let's say
37.5.
38, and here we'll have some more. 38 plus 28 is 58, and here we'll have 2 or something like this. Does this come to 2? This is 150 into 1 by 1200. By 1200. So this will be 20. This is like 7.5. Okay. And then here I must have made some mistake. This is 20.
This is 20, 22, 15 by 2 into 5, 75 by 2.
But the sum needs to come up to 60. I am exceeding 60. So
Okay.
that's
Sum
what.
needs to come to 16.
Yes.
38, 20, 58. And the last is.
So this one and this one doesn't
It should
match.
exactly come to 60.
It should exactly come to 60. Yes.
So something is 60 into 150 into 5 by 1200. So this goes to 20. This is gone, 75 by 2. And the next is
So this will be
60.
2 actually.
100. Which one?
This one, 60 into 200 into 2.
This is 2. This is
So
2.
this is not 20. This is 2.
This is 2. And the last one is 7.5.
So does it come up to, last one is
37.5 plus 7.5. 37, that's 7. 38 and 7, 45 plus 2. 47 it is come. It should come 20.
It should come to 60. So I think we've made some
60.
mistake. Let us
The
revisit.
second one, this is 20, 10. This is 20. And this graduate is 20. So that will come 60 exactly. 37.5 and 7.5 plus 20.
Okay.
This is okay. This is 20 is okay.
This is 58, right? 38
Yeah,
plus
58 plus
20.
2. It's not 2. 7. The first one is 37.5.
Yes. The second one
The
is
next
how
is
much?
20. Next is 20. And the last one is 7.5.
Why is the next one 20?
This is
4,
60 into 200 into 2.
20, yes.
By 200, this is 20. So 37.5 plus 7.5, it is 40.
This is the query. This is not 47. This is like.
No. This is
Something is off.
37, 40,
Something is
38
off.
plus 7, 45. this is 45. And this one is how it is coming 20. This is 600,
This one,
200
there's
into
some mistake here.
200 into 2. This is 60 is the sample size.
Sample
No,
size, yes.
60 is the sample size into 150, then 200 into 5. So 2, root 2 is okay. Root 2, then 400. So it is coming 65. It should come
It
60.
should come to 60, yes. Let's revisit.
5.
150 into
150 into root 20, root over 25.
root over
So it is
25,
5.
5,
750
750,
plus 400. That is
200 into
1150,
2.
and 150 into root 1, 150.
Okay, so this is not 1200,
It,
this is 1300.
this is not 1200. Yeah,
Yes,
this
yes,
is wrong.
yes.
Yeah.
Here we have made a mistake. I have made a mistake, sorry.
1300.
This should be 1300. So
1300 into, so it will go be 60 into 150 into 5 by 1300. So 90 into 5 by
so this is
13. That is
1300.
450 by
So
13.
undergraduate is 150 into root 25 by 1300 into 60. Graduate is 200 into root 4 by 1300 into 60. And doctoral is 150 into root 1 into 60 by 1300.
90 by 13. So this is 450 if we add up 13 plus 90 by 13. So this is 0, 5, 4, 9, 9, 18, 1, 3, 4, 7, 780 by 13. Yeah, exactly. 780 by 13 it comes.
Okay.
So it is 60. So the first one will come as 450 by 13.
How much will that be? 450 by 13. Okay, let me just write
13.
it out. So this is something 450 by 13.
Next will be 240 by 13.
Next is 240 by 13.
And the last is 90 by 13. 90 by 13.
Okay.
So
So
if
if
we
this
add
is,
all this,
if like 34.6,
yeah,
this is 240 by 13.
13 1 plus 13 1
It's like
11 1 0.
18.5 or
18.
something. Rounding up to one decimal places. Let me do it.
This exactly comes over 780 by 13.
Yes.
If we add up all
So
these three,
this one is,
780 by 13, so it will be 60.
yeah, it will be
780.
60. Yes. So for each, like if we round it up, let's say we'll have approximately seven
Somewhere
doctoral
7.
candidates.
7.
Yeah.
30,
This
34 plus 18, 51. 51, 52 it is, and this is, yes,
52, and this is 17.
53 it is somewhere.
This is
53 and 7.
1825, and this is 35, let's say.
Yeah,
Okay.
25, 35. So it's 60, is reaching 60.
Yes. So if we allocate 35 students here, so this will be a term of proportional allocation.
Okay, this will be proportional allocation.
Yes. Sorry, this will be name and
So,
allocation. I'm sorry.
name an allocation.
Yes, this will
Yes.
be name and allocation. We are just rounding it up. So,
Mm.
as you know, if we have zero point 0.5 and we have even, so that remains the same. But if we would have add odd, then it would
Mm.
have increased. Like simple
So that,
numerical
yeah,
things.
approximation we will do it.
Yes. So because I did not choose this carefully, I had to do this
Yes.
approximation. But you get how to do it, right?
Yes.
All right. Thank you. Now this was how you would calculate the samples.
name and
Name one
proposed.
allocation and allocate the samples. Now, what is the actual y bar st that we
Okay.
are trying to estimate? Stratified term that we are trying to uh, estimate, is it 1 by n summation h equal to 1 to h small nh y yes, summation small nh y bar h, is it this, or is it 1 by n summation h equal to 1 to h capital nh y bar h? Which one?
Y bar st.
Yes. Mind you, whenever we are talking of y bar st, we
Hmm.
are talking about an unbiased estimator. So, which of the two do you think is unbiased?
Actually, I made mistake in while solving this question.
Okay.
Unbiased mean
Unbiased meaning expectation of y bar st should be equal to capital Y bar. And that
capital
capital Y bar is summation yh
population.
bar into
Oh,
nh, h equal to 1 to h.
okay, and 1 is to h capital product of nh into y bar h. Biased estimated.
So, the entire point of revisiting this is that we have this
Yes.
natural tendency to replace everything capital by everything small, and
Hmm.
assume that that works fine. This is just to remind yourself that that's not the case always. So, if you have this one where I mean, by now it is familiar that all cap refers to population and all small y refers to samples.
Sample.
Okay, so if I have 1 by n small n h equal to 1 to h small n h into y bar h,
Y bar h.
and we take an expectation, so this means 1 by n summation h equal to 1 to h small nh expectation of y bar h. Now since we are doing
Here we are talking about only sample, no? H.
a small, so
Small.
small h is running from 1 to capital H, it is an index representing the strata.
Okay, right. This that is straight up. Yeah.
Yeah. Okay, so now expectation of yh bar, since within each stratum I am doing SRSWR, I know for that special sampling scheme y bar, the sample mean, is an unbiased estimator of the population mean. So since I am doing it for each of the strata, this one I can write as h equal to 1 to capital H small nh, this will be capital Y bar H. Do you agree with this?
Yes, it's okay. And it's this Y bar H.
So this part is equal to this part. Do you agree with that? This much?
Hmm.
Okay. Now this is not equal to 1 by capital N summation h equal to 1 to h capital NH y bar h. So let's say you have this is your strata 1, this is your strata 2. I'm considering 3. Okay, you have 20 samples here, 10 here, and 30 here. So in total you have 60 samples. Your capital N is 60. And you are drawing a sample of 10. Okay, and let's say you draw from here, you draw 5, here you draw 2, or let's say I should say you draw 5 from here, 2 from here. Okay, 5, 2, and here you draw 3.
3.
Okay, so now if I do NH by small n and NH by capital N, so this is 5 by 10, but this is 20 by 60. Okay, so this is how much? This is half, this is 1/3. Similarly, this one, this quantity, small nh by nh, this is 2 by 10, and then we have 10 by 60 for this one. So you see, and even if we sum it up, summation nh by n and summation nh by n, these two are not equal. I mean, these two are equal. I'm sorry, these two. One second. Okay, these two might be equal, but we are not only considering these. What I mean to say is that we are not only considering these and adding it up to its face value. We are also multiplying it with respect to the y bar h. So essentially what I mean to say is that 2 by 10 or what I mean to say is that 5 by 10 into y1 plus 2 by 60 into y2 bar plus 3 by 10 into 2 by 10 into y2 bar plus 3 by 10 into y3 bar, this one is not equal to 2 by 60 into y1 bar plus 10 by 60 into y2 bar plus 30 by 60 into y3 bar. You get the point?
Yes, yes.
So individual proportions, since they are varying, and we are not only considering these sums alone at face value, we are also multiplying the population average or the strata average with each of these terms. They are not equal, and this quantity here, 1 by capital N summation capital NHYH bar, this is actually my population mean, population Y. So coming back here, which one of this is correct? We can say now that This is not correct. This is the correct thing. Because if we give expectation over here, this will come out as capital Y bar H, and that is exactly what I want. Do you understand this now? Why I went ahead and reminded you of this. So this one is actually the correct Y bar ST. And we'll be trying to infer variance of this thing. So we'll be trying to infer variance of Y bar ST. In other words, variance of 1 by capital N summation H equal to 1 to H capital NH into small y bar H. Alright. Hello?
Yes, ma'am. I just lost my connection actually.
Okay, I understand. So what I was saying is that we should exercise caution while doing these kind of things, because most often than not we talk about variances and we forget the actual estimator. Okay, so keep in mind that y bar st is actually small yh bar. So for each sample, so to say in plain and simple English, for each of the samples, for each of the strata, we have the sample, we take the average, and then we weigh that average according to the uh, proportional representation in the population.
Mm.
Okay,
Yes.
fine. So once we are clear with the estimator, let us now look at the variance. And I would like to solve a few problems as we go along the way, so that we don't have to repeat much and we can move on to the other topics. So let us just do this. A university has a total of 500 students consisting of 150 undergraduate, 200 graduate and 150 doctoral students. So here we have this pattern. And since now we are not talking about the sample size allocation, let these be the numbers. Like anyway it will come as fraction, so we'll just calculate it and see what it gets to. Alright.
Okay.
I'm so sorry. Yeah. So now we have, let us just write down capital U, capital N, and these things. So capital NU for NU is 150, NG is 200, and
Is
ND
150.
is how much? It is also 150. Alright. Now we have
Yes.
been asked to draw a sample of 100 students.
100 students.
Okay.
Still use equal allocation.
Okay, so let me do, instead of 100, let me write down 90 over here, so it's easier. Okay. So here I have small n equal to 90 and I have equal allocation. So therefore NU should be 30, small ng is also 30, and small nd is also 30. Okay, so determined. Now the question is that from each category it will be chosen simple random sampling without replacement. So then find out what is the variance of the stratum mean in this case. So if we follow so coming back here, this is essentially variance of summation h equal to 1 to h nh by n into y bar h. Do you agree?
Yes, ma'am.
Okay. So here this means I can write it as variance of summation h equal to 1 to h small h, some weight parameter, into y bar h, where wh is nothing but capital NH by n. Okay. Now this means summation h equal to 1 to h. This is a scalar quantity, so we'll have WH square variance of YH bar plus double summation h not equal to h prime equal to 1 to h YH prime covariance between YH bar and YH bar prime. This is how a variance is distributed. Okay, so you will have like essentially the coefficient squared into variance, sum of all those, plus double summation, a covariance term with the respective weight weight scalars. Okay, now this part is actually 0. Why so? Because from strata 1 and strata 2 I am sampling independently. In the sense that if I have categorized my entire dataset into discrete groups, I am considering a random sample from group 1, then taking a sample from group 2, but between the samples or even within, I mean within will depend, but between the samples there is no dependence, in the sense that whatever I am selecting from, let's say, the male population doesn't matter doesn't depend in any way on the sample that I've collected from the female samples. Okay, no dependency between the samples. So that is the reason why we have a covariance term as 0. So this essentially boils down to summation h equal to 1 to capital H WH square variance of YH bar. And we are going to use, and since for each of the strata we have used simple random sampling, based on the sampling scheme we are going to tweak this and get the desired results. Is it okay? Alright, so let us just come to the question. So now we have this, assume the variance of satisfaction score. So S1 square is actually 5, S2 square is 4 and S3 square is 2. So now variance of y bar st is equal to summation WH square h equal to 1 to h variance of y bar h. Okay, and here we have seen that the sample random scheme, the sampling scheme for each of the samples is SRSWO card. So this one will follow an SRSWOR scheme. So how does the variance look like when we have an SRSWOR? This will be H equal to 1 to H, WH is square. So SRSWR for each strata. That means this formula but with every index. So we'll have small h minus nh by capital NH NH into SH square. Okay. So this will be WH is how much? WH is 30. So in each of these cases, since we have n as common, or sorry, this will not come here. So WU is 150 by 500, WG is 200 by 500, and WD is again 150 by 500. Okay. So here we have 150 by 500 whole square into NH is how much? 150. Small nh is how much? 30 divided by 150 into 30 into, here we have 5, plus then we have 200 by 500 is WH whole square into 150 minus 30 by 150 into 30 into 4 plus 150 by 500 whole square into 150 minus 30 by 150 into 30 into 1. So whatever comes up, that is the thing. Okay, this sounds good.
Yes, ma'am.
Okay, so for equal allocation, if I don't think I'm sure you have noticed this part
Yes.
will remain constant across data. Okay, for equal allocation. But this is going to change if we have different what do I say, if we have different allocation schemes, right? Now
Right.
same thing, if this problem is changed a little bit and we have the same setup, but here instead of equal allocation we have the changes here, SRSWR. Then how does this change? Variance of y bar st is actually summation h equal to 1 to capital H WH square variance of y bar h. So this part for SRSWR is summation h equal to 1 to H WH square ni minus 1 nh minus 1 by nh small nh into sh square. So this will be how much? This will be 150 by 500 whole square into nh minus 1 is how much? So this is 150 minus 1 by 150 into 30 into 20 into 5
into 5
plus 200 by 500 square into 150 minus 1 by 150 into 30 into 4 plus 150 by 500 whole square into 150 minus 1 by 150 into 30 into 1. Okay, so this part
Yes.
is going to change if we have a SRS WR. Alright, then let's move on to this one. Okay, I have written 2 over here, so I should have 2. Okay, similarly I should also have, so let me see what I've written here. I've also written 2, so here also technically I should be multiplying with 2. Okay, now what will happen, how will it change if we move on to proportional?
Proportional.
Okay, proportional, and so the thing that we should look up is proportional, and within each stratum what is the sampling scheme. Okay,
Yes.
proportional means okay, so let's do one thing. Let's make the parameters same as the previous question so that we
Equal.
don't need to recompute. Okay, so where was the proportional thing? Proportional allocation. Okay, so this one had 100, 200 and 300 students and we sampled 60. So we'll have 100, 200 and 300, right? 100, 200 and 300. And this is a total of 600 students and we drew a sample of 60. Alright.
Yes.
And what was the variance composition at that point? Even though we don't need it for proportional allocation. But let it be like this, okay? Just to
Yes.
confuse you, let it remain like this. So, while allocation, we won't need this variance. But to calculate variance, we definitely need this. Alright? So, SRSWR, variance of, oh no. So, variance of Y, oh my goodness. Variance of, yes, Y bar ST summation h equal to 1 to h wh square variance of y bar h. SRSWR variance of nh minus 1 by nh small nh into sh square. Okay, so wh square, wh was how much? capital NH by capital N. So this will be 100 by 600 whole square into NH minus 1. So 100 minus 1 by 100 into small NH was how much? We calculated earlier. It was this one, right? So I'll just copy this here. So small NH was 10. So into 10 into 5 plus again 200 by 600 whole square into 200 minus 1 by 200 into, here how many we have? We have 20 into 4 plus 200 plus 300 by 600 whole square into 300 minus 1 by 300 into 30 into 2. Is it okay? All right.
Yes, ma'am.
Okay, sir. So same thing if we go for SRS WOR, how will it change? Same thing, but here we want instead of WR we want WOR. So this parameter is going to change. Instead of NH minus 1 we are going to have what is happening. Okay. So we are going to have NH over here, and that is going to make all the difference. So this will be 100 minus 10, this will be 200 minus 20, and this will be 300 minus 30. Okay.
Right, ma'am.
Right. All right. Now let us move on to the last one, that is name and allocation. Okay, we did a calculate name and allocation with the previous one. Let me just pull it up here. So this is what we decided, right? 7, 18 and 35. Same thing. 500, 150, 200, 150, 500, 150, 200, 150, and we are selecting okay. So we didn't notice here we did all our calculations with respect to 60 students, whereas we should have included 100 students. Alright, then let's change this question to, so here small n was assumed to be 60. Okay, Here small n was assumed to be 60. Yes, so this was the proportion calculated that you have 60. So let's say I am going to write it out here. ND in undergraduate is equal to 38. In doctoral or in graduate was how much? It was 7. And in doctoral was 7, ND was 7, NU was 38, and NGA was 18, right? Or something. 30. Okay, so this one was 35. No, something I can't see here. So here we had UG 35, G we had 18, and this one, okay, G we had 18, and this we have 35. Okay, something like this. So now name an allocation and SRS WR. Variance of y bar st 1 is equal to summation h equal to 1 to h wh square variance of y bar h summation h equal to 1 to h yh square variance of this thing under, so this is nh minus SRS WR by nh small nh into S1 square. So this is actually 150 by 500 whole square into 500 minus, sorry, into 150 minus 150 into small nh is how much? 35 into what was this? Name and allocation 2541, right? So here we had 2541. Mind you, all the parameters have to be same between these two questions for these figures to work. Okay, so here we have variance of yh bar s1 square sh square into 25 plus 200 by 500 whole square into 200 minus 1 by 200 into 18 into 4 plus 150 by 500 whole square into 150 minus 1 by 150 into 7 into 1. So whatever it is, that will be your variance. And the same thing if we want with respect to WOR, then the only change that we need to do is here. So instead of n1 minus nh, this will be nh minus small nh. So this will be 35, this will be minus 18, and this will be minus 7. Is this okay, the sampling schemes and everything?
Yes.
Okay, sir. So now that we have done this, let us move on to use the R software and see what we can do with it. Right? Please let me know if you can see my R screen. Is it here or can you see it? Is it visible? Okay, I think it's visible. So I'll just start. Okay. So before
Yes, ma'am.
okay, thank you so much. So before moving on, um, yeah. So I would like you to install these three packages so that we can use them while we are on our quest to solve a few practical problems on stratified sampling. Okay, so this is a custom code that was also provided in the lectures, and we can make use of this to stratify our data set and perform a stratified sampling. Okay, the main function or package that we need is for this, the first exercise are these two packages on strata and sampling. Now in order to use this stratified format, we need to have a data frame, a df. Okay, and here they have mentioned what each of these arguments mean. So specify your data frame and grouping variable as column number as the first two arguments. Decide on your sample size. For a sample proportional to the population, enter size as decimal. For an equal number, enter size as a whole number. So this particular stratified sampling will only work for equal and proportional. Why do I say that? Because it doesn't look like that it takes the variability into account just by the nature of or the structure of this mm, function. So it should take equal and proportional allocation into account. Alright, I'll save this so that I'm not going anywhere. So this should be week 7. Yep, okay. Now what is this function doing? This function is calling these libraries and then creating a temporary ordered or sorted data frame with respect to the column that we want to be used as a stratifying category. And then if size is less than 1, then they are doing a sort of proportional allocation, right? So this is how they are taking that into account and adjusting the sample size for each of the stratas. And if size greater than equal to 1, here they have mentioned if we use proportion, if we use less than 1, then they are going to use the proportional scheme, and if it's greater than 1, they are going to use the equal scheme. And so this is how they are performing the equal thing. And then this function strata is actually using the sorted data frame and then drawing samples with respect to the categories and the sample sizes, implementing a SRS WOR scheme. So let us just first test it out, and to do that let us first create a data frame. So if we closely monitor the example, or let's create the one that we have used here. So I am going to have a data frame of 500 individuals, right? Okay, so I could say let's say my ID equal to D, or I should give, let's say, C 1 to 500. Okay, let's mimic the last example that we have seen. Okay, now category B or in other words, student type is equal to, let's say, we replicate undergraduate. How many times? How many undergrads did we have? 150. And then let us replicate graduates. How many did we have? 200. And then let's replicate, did we have? Doctoral into 150. Okay, so 500 done. And then we wanted to have the y values, or let's say let's not have the y values as of now. So let us just make a data frame with respect to these two values. So that one equal to data dot frame, let's do this id and type and see what we get. So we have this data where these are the IDs and these are the types. Alright, now let's say we've decided on how many samples we are going to take, and let's say we are going for an equal sampling technique.
Yes.
Okay, so if we are going for an equal sampling technique, if we use stratified, okay, let me just run this and load it into memory. Okay, so this is stratified, and then we have to add the group variable as column number and the size. So if we give that one and write this as type, and then give the number, let's say equal, we wanted so 20. So let's see, cannot xt from data frames, why is that so? So if we give type cannot xt from data frames, do you get this error? Let us find out what's the source of this error. Okay, so this looks like that we'll have to give the column number. Oh no, even then it's not happening. Okay, df order df comma group. Okay, it should work now. Okay, it did work. So instead of so the point I change is here. Okay, so temporary df order df, so what it is doing, order df this group. So I'm going to print this so that you get it. Okay, so print temp, and then let's find out how things are working. So the initial data frame, if I do a head of data frame, then this is how it looks like. All right, 1 2 3 4 and u something like this. Now when I'm doing stratified, what am I getting? So that column where we give the print statement, what it is actually doing is that this is at first it is taking the group column in my data set, then it is ordering it with respect to the group column. So I'll have D first, G later, and then U at the end. And then once this order is going to give me the row indices. So now I am storing these uh, indices accordingly so that my temp array becomes a sorted one. Okay, so now I'll remove this print statement. So here we have, and we are taking stratified 20 samples from each. So if you check here, so stratum we'll have 1, we have 3 stratum, 1, we have 2, this is strata 2, and here we have strata 3. Okay, 20 samples each, 1 2 3 4 5 6 7 8 9 10, again 1 2 3 4 5 6 7 8 9 10. So 20 samples each from each of the stratum. Okay, and what are these probabilities? Can you tell me? Let us find out what is it actually reporting. So this is a sampling technique without replacement. Now if we wanted the same thing with replacement, let's find out this thing. Sorry, stratum 1, no, none of the units are repeated, but if we did a with replacement thing, yeah, perhaps we would have gotten repetitions. I'm not able to see it now, but perhaps we would have had that. Okay, we don't see it here because we have very less sample size, but perhaps, but maybe we can see that later. Okay, now this is how the uh, strata command looks like. You can go in and check what each of these things mean. But anyway, the thing I should be concerned about is which ID unit I am considering. So ID unit is nothing but the indices in the sorted array. So don't bother. The thing that should be that we should focus on is the ID column. That's our primary key, and we should consider samples with respect to this column. Now if we use
हो गया 2 बार.
instead of 20 samples for each group, if we consider DF group size, alright, so if we now need 0.1, so let's see. So this is sample 1, this is sample 2, this is sample 3. Alright, so this is how we are going to use the stratified um, sampling to continue with equal and proportional allocations. Alright, so now that we have learned about the sampling thing, I just want to know one thing, whether it is clear that it is performing proportional and equal allocation or not. So is this part clear, or do you think it's still little fuzzy?
Please say again, ma'am.
Yeah, so did you understand this part, that when we are tweaking this into constant numbers, how it is changing?
Yeah, I further need to practice this, ma'am.
Okay,
I've got it, but I need some practice.
I see. All right. Okay. So, uh, once we have learned this strata thing,
Okay.
we'll also go over to this, or we can go over this SV or survey package, and that is a little more complicated. The Oh, okay, we are running out of time. So I'll do one thing. For
Yes,
the
ma'am.
next session, I'm going to create a dedicated program for using this survey package, and maybe in the next session, I'm going to discuss that in details. For the time being, I just want to quickly go over little bit of bootstrapping concepts that will help you with the assignments, if that's okay. Okay, so
Okay.
I'll come here. Fine. So now that I'll I'll go over on these stratification with R in details in the next session. So I'll just keep it here. Next session, detailed stratification example. with us. Alright, so right now I'll just touch up on bootstrap. So bootstrap is a resampling scheme where if we have, let's say, a sample, and this is my population, from here I have a sample. Now y bar is easy to compute, variance of y bar. Also we have closed form solutions. But oftentimes it happens that the variance terms are not that easy to compute, both analytically and mainly analytically. Okay, and we could have different forms assuming that my sample size is large, and we could take a whole lot of assumptions into account. But for smaller sample sizes, those assumptions usually fail. So this is another such scheme by which, making use of which, we can um, uh, get estimates of quantities which are hard to derive. Okay, so for example, we usually work with mean, but instead we could also work with median or coefficient of variation, which is nothing but mean by SD. So deriving variances of these forms are extremely difficult. So we use bootstrap. Now what is the main goal of bootstrap? The main goal is, if we have, let's say, 1, 2, 3, 4 and up to 10, if this is my sample, or I should write in this manner, let's say I have 1 to 100 in my population, and I have drawn one sample which is from this population. So let's say this is B1. Okay, so bootstrap thing is nothing but resampling from this population again and again, and then computing the statistic for each of the bootstrap samples. Okay, or let's say not from here, so from the population we are sampling again and again, and then we are considering the distribution, and then so for B1, B2, B3 we'll have the statistic, let's say T1, T2, T3, and the goal is to match the CDF of T1, T2 and T3 to the actual CDF. And by CDF I mean it's the cumulative density function. Okay. So we have an original sample. If this is my original sample 1 org, from here I am going to get bootstrap samples B1 to Bn, calculate the T1, T2, those kind of things, All right, and then okay, so from sample, the original sample to bootstrap sample, we are going to use an SRSWR method. So here we'll have uh, n estimates, and then we'll be working on this distribution to estimate the variance, standard deviation, standard errors, confidence intervals, and so on and so forth. This is the main goal of bootstrap. So for example, if we wanted a median, let's say, and we have been given that this is my sample, so we'll resample again and again and again from the same sample, calculate the median for each, and then we'll take a mean of the medians, and then we'll calculate the standard error. And assuming that this distribution closely matches the distribution of the original parameter under consideration. Alright, now mind you, you should be careful that since this is resampling, if your original sample didn't have a particular element, then that element cannot appear in your bootstrap sample. If it does, then you are doing something wrong. Alright, and empirical CDF, whatever I am saying that these distributions should match, empirical CDF is that cumulative function, like it should work like this, that probability y less than equal to y. This is your CDF. Now if you just base this CDF with respect to your problem or observations, then you have an empirical CDF. So if I have to give you an example, um, mm, so if I have to give you this, so if I have to, where is the cursor? Yes, so instead of uh, writing the actual probability if we base this on my existing uh, observations. Whatever I'm going to get, that is the empirical probability. Now let's say my y can take values between 0, 1, 2 to 10. Okay, so let me consider this discrete case. So this is y, okay, and I'm seeing I'm going to count cases uh, and divided by total. So let's say I have, so if I have 60 observations, let's say, and I make this, let me just find out the minimum and maximum. Let's say it starts at 0 and ends at 60, something like this. Then I'm going to find out, or let's say I have marks like this at intervals 0, 10, 20, 30, 60. Okay, let's say I have my y axis as this. Now here I'm going to count number of observations less than equal to 10 by 60. Okay, and then this stepwise graph, which will start from 0 to and end at 1, this is actually giving me my empirical CDF for a case where I have the x values, x axis discretized. Okay, so let's say if I have to frame it in this manner, so let's say I have a call center and I receive 60 calls daily. Okay, and I monitored the calls at these particular stages. So then number of calls less than equal to 10, I'm going to count divided by 60, and that will be the probability that I have less than 1 by 6 calls, or probability I have less than 1 by 3 calls, something like this. Okay, and these will keep on adding, and here this is how you are going to get an empirical CDF. So I understand this is a bit rushed, and I would have liked to provide more information, but I'll do that in the next session because today I'm running out of time. And then
Yes, yes, ma'am.
I hope this much will help you solve this week's assignments.
Yes,
But in the next week, I'm going to go over the CDF, empirical CDF concepts and stratified sampling in greater details for the ease of understanding. Okay, thank you so
right.
much for joining, and I really
Thank you.
appreciate your patience.
Ma'am, just
Yes,
one question I want to ask.
yes.
The assignment dates are scheduled already. If we suppose we fail to submit on the due date, so
If you want to modify, I think you can do that by resubmitting. The last one will be taken. I hope so.
okay,
But you can confirm it with the NPTEL team. I don't know about this here. But in any
okay,
case, if you do not submit, then I don't think it will be counted towards your grade.
okay. I mean, if by the last date,
Yes,
the due date,
yes, yes,
if by the due date, if I don't submit, then that will not be counted.
yes.
Yes.
That is the usual norm. But if you do have genuine queries, you can perhaps reach out to the NPTEL team. But yeah, I would urge you not to miss the assignments if you really want the certificate.
Okay, okay. That
Okay.
I will submit it. One second.
Okay.
Thank you very much.
Thank you. And I think you can resubmit. The last one will be taken, but please confirm it with the NPTEL teams. They would be able to tell you in greater details.
Thank
All
you very
right.
much.
Thank you so much, sir, for joining, and
Thank
I'll see you in the next week. Bye bye.
thank you.